Back in San Diego. When I left San Diego, this was about the time when Terry arrived. Terry tried to be very kind to everybody. So one way of getting to know everybody, he invited most of the neuroscientists for a barbecue to his house. He didn't realize that making a good barbecue is much more difficult than computational modeling. So the chicken was burned from the outside, but was not ready from inside. So I helped him out, and I shared a trick with him. I don't know if you remember. I do remember that. And in return, he became my friend and good supporter ever since. And the reason why I remember all these details is because they had some utility to me, and I have a mechanism in my brain that allows me to select those things that are important and get rid of those that are not important. So we all agree with that, and we all experience this, that there are about 15 savants in the United States who cannot forget anything. They remember everything. You can watch them on 60 Minutes by Leslie Stahl, had a wonderful movie about it. But those people don't hold a job. Rain Man couldn't even tie his shoelace and so on. So there is a lot of merit that you don't remember everything from what I'm going to talk about. There will be very selective moments, and this is the time where you will pause and say, oh, that might be interesting, and then you remember. And I'll give you away the mechanism for this, and this is the hippocampal ripple, which is slightly different than what Eric was talking about, but it has the same problem, same issues. Now, before I get to the punchline, I'd like to tell you a few things about ripples. So the hippocampus is a wonderful structure in a sense that is capable of dividing the behaviors into two major categories that psychologists and physiologists talked about for more than 100 years, starting with Craig probably and then Sherrington, that there are preparatory behaviors or exploratory behaviors, and the entire goal of preparatory behaviors is to get to goal. And when the exploration is over, you stop, and the brain changes, and this is also called terminal behavior or consumatory behavior. So when you have an electrode in the hippocampus, it's pretty straightforward to tell what the animal is doing. You can blindly look at the electrical activity in the brain, and you can tell the animal what is the animal doing. During theta oscillations, the animal is moving around or is in REM sleep, while these sharp waves that are occurring at the stratum radiatum of the CA1 region, then this is the time when the animal still is engaged in consumatory behaviors, including sex and defecation, drinking, and non-REM sleep. The reason why I'm showing these slides is I recorded it here, not so far from here in the MSB building in UCSD. That was a while before, but then we discovered that, at the same time when this large sharp waves occur, which is nothing else but the CA3 pyramidal neurons generate the burst that Eric was talking about, and then they transmit this output as a depolarizing force to the apical dendrites of CA1 pyramidal cells. So you can read out from the extracellular LFP very nicely that this is an EPSP-IPSP combination, and the neurons that are exciting the pyramidal cells also excite interneurons. And this tug of war between excitation and inhibition is producing this ripple activity. And the reason why I call it sharp wave ripple is because it's a complex wave. That is, it has one component and it has another component. It also controlled by a variety of different things, and what I'm showing you is, again, relevant to the first talk, is that how do we distinguish between what is a ripple, what is not a ripple, what is a gamma, and what is not gamma. What you can see here is the slow fluctuation of acetylcholine, but it could be norepinephrine or anything, and at a particular rhythm during non-REM sleep, and the dashed line show the occurrence of ripples. And you can make it by eye that the highest probability of ripple occurs when the subcortical neuromodulators are at their minimum. So ripples are not triggered, ripples are not induced in a sense, they are released. At the time when the grip of the subcortical neuromodulators is at minimum, you can cut the femur phonics, for example, and you've got lots of ripples. So this is an interesting thing, and of course you can do the other way around. You can release artificially acetylcholine and you can kill ripples. This is the safest way to kill ripples. And what is not obvious from the figure here, that you can release a very small amount of acetylcholine in the hippocampal circuitry, and you won't see anything interesting except that there are no ripples. So you can completely wipe out this. The good news about ripples that they are preserved throughout evolution, at least in mammalian evolution, but we can go back a few million years, and even in the Australian dragon is there, people have described it in pigeons or in birds, and so on. They are the most synchronous patterns in the mammalian brain. So that must be very important. And of course, the hippocampus plays its fire because it generates these very powerful ripples. And if something happens, then its first cousin will appear, which is called the epileptic interictal spike. Perhaps one of the reasons why the hippocampus is the most epilepsy-prone part of the brain is because it's already tuned to do maximum firing. So what is the consequence of this very powerful synchronous activity? That the consequence is that it can reach to very large areas. So you can see a whole list of areas that are affected by hippocampal ripples, including the neocortex, thalamus, and midbrain. The effects are slightly different, and so on. And this is not only in the mouse, but also in monkeys, as Nikos Logothetis has shown in a beautiful fMRI combination with physiology. Okay. So they are not only affecting the rest of the brain, but the rest of the brain is affecting the ripples. This is a typical organization of the brain, that whatever is computed locally is broadcasted globally, and the local computation is always under the global control. So it's under the control of sleep spindles, under the control of up and down states. So this is a power spectrum centered on the occurrence of the ripple, and you take plus minus 30 seconds, a very long time, you do a power spectrum, and what you see is that whenever there is a sharp wave ripple, then it's very likely there is a spindle, and the phase of the spindle times the occurrence of the ripple in the hippocampus. And the spindle timing is under the control of a slow oscillation. This is called the up and down state, or mutual stereo, they call it the slow oscillation. And in turn, it is under the control of an even slower 0.1 hertz oscillation. It's the Bolt signal in humans. So you can see that there is a connection between the two. Then usually we and the computational neuroscientists are talking about is that there is a source and there is a target, the hippocampus and the neocortex. They have a bidirectional dialogue, but we assume that these two structures are point sources. So there is the hippocampus, which is a point, and then there's the target, which is the neocortex, is a point. And of course, that's not the case, because time in the brain is also space. Whenever it takes something time, that the activity can spread. And this is a better illustration of this, because there are patterns that it's very difficult to find standing waves in the brain. Everything is always traveling. In the neocortex, long time ago, Dr. Steinovsky and his group showed very beautiful, funny patterns in the spreading of ripples, of spindles, and up and down states have been shown. And the hippocampal theta, the sharp wave ripples in the hippocampus are traveling. Now, this is an interesting thing, because when you have two chaotic systems, it is very difficult to make predictions what happens within that system when you have you have access to looking at only one. But if you connect the two chaotic systems, then knowledge about the timing of events in one can give you an intelligent guess what's happening in the other one. And this is what I'm going to show you in a second. So this is just an illustration that indeed activity is going from one way to another. And what we have done traditionally is we put an electrode here and we put an electrode here and say we are studying hippocampal neocortical communication. Obviously, it's a little exaggeration, even if the electrode is the prefrontal cortex, because it's just one and the layers are very different. It does make a difference where you are recording from, whether it...
Where are these gray areas?
Just a second. Okay. So this is another view. This is a mouse brain. It's a wide field imaging method combined with physiological recording, electrophysiological recording in the retrospadial cortex from the contralateral side and from the hippocampus. And once you do that, then you can look at time in one situation, another, the time and space in the target area, which is in the neocortex, and you go and look at the bidirectional interactions, such as what is the relationship between sharp phase and up and down states, what is the relationship with ultra-slow and infra-slow oscillations. Here is just one example of the movie. What I'm showing here, that the ripple occurred here, or at least the peak of the ripple is occurring at time 0. Prior to the occurrence of the ripple, there is a good chance that in the mouse default network system, centered with the retrospadial cortex, I always lose my mouse. So yeah, this is good. So starting with the retrospadial cortex is about 100 milliseconds earlier. It seems that there is a cause, if you want, there is a trigger that starts in the neocortex that times the occurrence of ripple. So then we explored this a little bit further. We took the timer in the neocortex as the down or the up-down transition or the down-up transition. And we plotted various things there. So the first thing we are looking at is what happens if there is a ripple in the hippocampus. What is its relationship to the up-down states? And the answer is, what is plotted here is the probability of these up-down transitions at the time of the occurrence of the hippocampal activity. And we can see in a very short period of time, less than 100 milliseconds, the probability is very much higher, and depending on the amplitude. The larger the amplitude of the sharp wave ripple, the higher the probability that it can ledge down the up state to a down state. Now we can look at this game in the opposite direction also. Said, well, when there is a down-up transition, then occasionally, somewhere in the cortex, there is a very synchronous activity. It's called K-complex. Now, this K-complex can go to the entorhinal cortex, and the entorhinal cortex does something with the hippocampus. And about 120 milliseconds later, this is a very long delay. It is not about conduction delay. It looks like a rebound activity. But again, the timing is very high. Depending on the magnitude of the K-complex, you can see there's a high probability of sharp ripples here. So it seems that there are several types of sharp waves. There are sharp waves that occur on the up state. There are sharp waves that occur at the down state and at the transitions. And Maxim will talk about this in his talk in a few minutes. So that's a good thing, but that's not what made hippocampal ripples famous. What the excitement is the spike contact, because it turns out that whatever the ripple, the spikes in the ripple do have something to do with our daily experience. So this is just an example about the waking ripples. This is an animal that is, in this case, is a rat that has 13 place cells. Place cell 1, place cell 13. It has a very nice sequence, as you all know. The interesting thing is that before the journey, before the animal starts, it is pausing a little bit, and when the animal pauses, you can see a ripple. And in this particular striking case, you can see that all 13 pyramidal cells fire in a short period of time, and in the same sequence as it will evolve later on when the animal is traversing the alley. And then a few seconds later, when the journey is over, this pattern is occurring again, but now it's in a reverse order. And with some fantasy, we said, what's happening here is that this is a subconscious, preconscious, or whatever you term you use, priming of the circuitry, and that selects or enables to select a sequential activity that evolves internally, and this is the reason why you see this sequence. And at the end of the journey, you can recapitulate, if you want, and then you play things in the reverse order, and you can call it memory. Now, in English, it's an interesting thing that you say, there is memory, and there is planning, there is imagination, and things like that. These are very different words. In Latin and in some other languages, such as Hungarian, they are not so different. When you say prediction and postdiction, they are not sounding very different. Now, the interesting thing that happened over the past decade, I would say, or a little bit more than a decade, is the recognition that those structures that have been traditionally assigned to memory processing are exactly the same ones that are involved in imagination and planning. So there is no real physiological justification for that. By the way, it was Denis Hassabis, the latest Nobel laureate, whose PhD work was about this. In fact, he was the first one who showed that there is a nice relationship between the two. So we know that. I don't think we have sound here. I can try it. Did you hear that? Okay, then I go back. There, little ripple, there's a nice, beautiful ripple, and then we're stationary. Now it starts moving in a second. And the hippocampal theta is also a nice mechanism of compressing this information, because you can tell whether the animal is past a particular spot or is going to somewhere. Again, in one single theta cycle, there are the sweeps rather than separation of past, present, and the future. And then I go to the end. Somewhere here. And then you will see, oh yeah. There was another ripple at the end. So if this, the idea was that actually I conceived it here when I was in San Diego. Here's another story with Terry. I'm not sure it was you or somebody else. When I talked about it in a I think it was a Salk meeting, then I said, oh, you have to give a seminar. So I gave a chalk talk, and the chalk talk had no more than 6 people, I think. One was Terry, the other one was Pat Churchland, Francis Crick, and maybe 3 more. And they interrogated me for a long time, and I said, oh, this is a good pattern. This was the time of LTP. We were very excited. It was 200 hertz, or close to 200 hertz. That was the best frequency, and so on. And said, oh, this is fantastic. This is the natural pattern for long-term potentiation. And of course, it took many laboratories to really prove or at least move the idea forward. But one of the key things, of course, is to get rid of something or add something, a gain of function, a loss of function. So is a loss of function if you can if you allow me to get rid of all of your ripples tonight, then you won't remember anything what I was saying or what the other speakers were saying today. So this was one early experiment. But we can go the other way around, is that we noticed that there are almost everything in the brain is log normally distributed. There are these big tails, Eric. So when you said, oh, there are only few of these things here, you have to pay attention because the tails are sometimes very important. So the duration of the ripple is log normally distributed. The inter-ripple interval is also log normally distributed. So there are very, very few of these events, but we thought it may be interesting and important because when you put an animal into a novel environment, then the probability of these low frequency events, but low incidence events, is getting higher. If you train an animal in the same apparatus, but the memory load or not memory load, again, the longer ones are winning. Even in the same paradigm, in a T-maze where the animal has to make a choice and sometimes make errors, when the animal makes an error, when the animal has a correct or an error response, during correct trials, the ripples are longer. So that's good. So can we make ripples longer? And one way to do that is just optogenetically manipulated. And there was a little discussion after Eric talked, how these ripples are generated. Ripples are generated by many mechanisms. You can see ripples in the lateral septum, which is all GABAergic. You can see ripples in the mammillary bodies, which has 100% glutamatergic, and other places. And if you optogenetically activate neurons almost anywhere, the response will be a ripple for perhaps the same mechanism that you talked about, refractoriness and synchrony and things like that. So we did that, and we asked, okay, what's happened here? And what happens after this is summarized here, is that when an event happens in the brain, because of these constraints and connectivity, the initial condition determines almost everything. So if the animal's in its mind said, I came from the right, now I have to go to the left, and there is a release of these ripples, then those events generate an initial condition which is biased from where the animal came from, and it will be a consistent one in every single trial, and then it's usually showed, and then the priming is either just here, the little fragments. But if we add an additional time there, then the continuation of this event will determine or will be biased by the ongoing sequence already. So that's the speculation. And so when the sharp waves are prolonged, it should improve memory, and this is exactly the case. So when we have longer sharp waves, hooray, this is a lot longer. Last case, this group that has always 100 millisecond longer sharp wave ripples learn better. Now, this is just a summary, and then I'd like to spend a few seconds about how we, the community, showed that indeed there is a relationship between waking sharp waves, sleeping sharp waves, waking experience during theta, and so on. What we typically did, and that was an interesting and important step forward that Matt Wilson showed, that these ripples contain a lot of spikes. In your brain right now, about 1.5% of the neurons fire in a single theta cycle is 100 milliseconds. But when you have a ripple, it can go anywhere between 5% to 35%. That our champion was 35%. So in that, a lot of neurons can fire together. Now, what we usually do to find those neurons that were relevant to behavior, you take a template. The template is usually static ones. I showed you a sequence of place cells, so you have 7 or 13 or 50 place cells, and you've got this template. And you're looking for exclusively those neurons that are happening there, that are happening in the sharp waves. And you said, oh, that's a replay. The problem with that is that many people, many laboratories try to make a link between these physiological patterns and what's going on online during learning, when the animal is actually performing. And there was no good method. So I try to show you a possible solution. So we are using a cheese board maze, which is a very natural behavior. Mice learn this at the same speed than rats. You can hide 2 or 3 or 5 rewards here, and you can change the location every day. So there's a new set of learning every single day. And the goal is that just to find the 2 rewards and come back. Now, of course, you can have various ways of detecting whether the animal learned or not. The learning is very rapid. In 2 or 3 trials, the animal already knows the positions. And we can check also what happens in the physiology and what happens with behavior and what is the relationship between the two. Because prior to learning, we can test the animal in the environment where this is the future bait, the future reward sites. But there is no reward here, there is no reward here. These are the probe trials before and after for about 10 minutes or 15 minutes. The animal is just searching around, and you would like to see whether there is some behavior readout of the memory. And the answer is yes, the animal remembers that there was a reward. It's almost like the what is Mordeway's task. Now, what we do between these manipulations, we put the animal back into the home cage, and the animals can sleep there for approximately an hour. Now, we have a good thing here, because now we've got lots of spikes. The enemy of system neuroscientists is the few spikes. So we have to generate always a paradigm when the number of spikes that we can do statistics with is sufficient. So what we try to do now is we go backwards. Rather than taking a template, we take the difference between sleep 1 and sleep 2 and see what we can do with it. So these are the ripples before, these are the ripples afterwards. Then this large number of neurons could be brought down to a few dimensions only, and then we can look at a subspace that is related to what happened before learning. And then another subspace that happens after learning. And then you can look at the difference between the new subspace and the old subspace with the relatively, not new, but in neuroscience, relatively new method, contrastive PCA. And you just subtract the majority, which is a common variance. So let me show you now that what is the advantage of all this is now that you can have these two subspaces, and they are different set of neurons, and then you can ask in every time window which one is dominating. So you can have a continuous readout of the old and the new in all behaviors. So this is what we do. Now the animal is moving physically here from across the space, because we were able to separate very contrasting patterns of activity that relates to the rest, or the sleep 2 or sleep 1, that is after or before, or the new and the old. So this is, you can see, this is a couple of theta cycles, and even within theta cycles, you can see that which one is dominating, and then you can have a time series of what's happening. Now, once you have a time series, that you can go from trial to trial, and you can see that this is the old subspace, this is the new subspace, that indeed there is a gradual learning process. We can do also the same thing, going back to tie it back to behavior, because now we can ask is that, we already demonstrated in the previous slide that the animal learns, that evidenced by the number of crossings here in the reward area. And this is also true in the hippocampus, in the hippocampal physiology, that the new subspace is dominating here and in this new explorative behavior. Even though animal is moving, there are no sharp wave ripples there. Okay. And once we have the contrasting values, we can also ask something that was difficult in the past, and I think this is new. Not only how is behavior progressing during learning, but how far the animal is from the reward. So if we have a U-map, and then if we color it according to distance from here to here, you can see that the old subspace is not very informative. But the new subspace is pretty informative, and you can show it quantitatively in a different way. Namely, that what happens is that the old subspace has the same amount of error all the time. It doesn't matter whether the animal is close to the reward or far, but the new subspace is getting better and better and better as the animal is approaching the reward. Now, I have showed two things so far. One is that the progression of learning is reflected by all the new subspace. Now I showed that the proximity of the animal to the reward is also changing. And now we can combine the two and say, this is a product of the two. Initially, trial 1, trial 2, trial 3, the old subspace dominates, and then as the learning occurs, it is already expressing 5 centimeters, 10 centimeters as soon as the animal is getting close to the reward. But with the number of trials increasing, then the distance that allows prediction of the position of the reward is increasing backwards. So from the reinforcement, there is a travel backwards of the activity in terms of the probability of predicting where the reward is. So summarizing what I had said so far, the new subspace is an interesting approach because it satisfies the criteria, what we can call learned activity. It emerges with learning, and it's always better near the rewarded area. They are reactivated in the rest 2 sharp wave ripples, as I showed. This was the starting point. And they are also, they predict the subsequent memory retrieval. So finally, we can tie this pattern, the sharp wave ripple, to something meaningful, which is learning. Now, probably many of you in the room know that sleep is good for learning. Sharp wave ripples are probably the most important carriers of this. And consolidation typically happens during sleep, non-REM sleep. But coming back to my main question here is that how do the ripples know during sleep which of the many experiences that we had during the day or during previous experience have to be replicated? So this is the question that we ask with Winnie Young and Roman and Chen Shun, and we had to do a couple of things. One of the things is to increase the number of neurons that we can record from. To make the long story short, if you would like to do this kind of analysis that I'm going to show you, you need at least 100 neurons. If you have 50 neurons, then it's super noisy and we don't get very far. So in order to get 500 neurons, or at least 400 something, then we use this, we call it Janus phase electrodes. They have recording sites on both sides, so we have a panoramic view of what's happening around the electrodes in a cylinder. And then we can record from there. Now, the good thing is that the more units you have, the more crispy the picture will become, and we don't need a lot of statistics. You can exactly read out where the animal is by just projecting back the sequential activity onto the maze. So at every single time point, almost every single 100 millisecond or 200 millisecond, which in every single theta cycle, you have a very good guess where the animal is in the environment. Now, this is fantastic, but nothing new. And John O'Keefe already got a Nobel Prize for it. But what I'm going to show you here is a slightly different thing. So this sequence is the same, and you go from 1 to 70 trials, and it's the same, or at least similar. But in philosophy, know that philosophy tells us that similar is also different. So maybe that slight differences are also very important. So indeed, in the similarity, you look at various trials and said, oh, trial 1 is just like trial 70. Again, Eric, everything is the same, but just 1 or 2% is different. But so in this case, this neuron fired at the beginning of the trial and got lousy by the end. This other neuron actually shifted its place field a little bit by the end of the trial. The third one that I'm showing you that was very silent at the beginning and formed a place field at the very end. Initially, we thought this is just a drift that people have described and so on, and I'm telling you and showing you it's not the case. So now we can do we can go from 420 dimensions to 2 or 3 dimensions, and we have used 7 different methods, but they are pretty much the same. So now, using UMAP, for example, we can make this judgment that every single time window, which is 100 milliseconds, we can project it on a 2-dimensional space with UMAP and said, okay, this point corresponds to here, another point, another point, another point. And we already observed that this is an interesting pattern. It's not exactly a figure 8 maze, but it has a reminiscence of that. It's not random. It has a good structure there. And if we exploit the fact that for every single moment, in every single theta cycle, we know where the animal is, then we can color it, and you can see that there is a nice neural manifold that tells you where the animal is at every single point. That's, again, a confirmation of prior knowledge. Everybody knew that. The novel thing here is that we ask that there is another variable here, that the animal covers this territory 50, 70 times in a day. But every single time, the patterns is slightly different. Can we, the experimenters, we are not at the brain yet, but can we, as the readers, tell which trial the animal is in? Now we colored from 1 to 70 in this session, and you can see that the pattern is indeed consistent. It's not random. It is a progression from 1 to 70. And then that's good. That's very important information for the reader, in this case, the experimenter. Now, can the other reader, the brain, also notice this difference? Now, to do that, our reader could be the hippocampal sharp phase that comes after exploration. Now, the hippocampus is a funny device. It is like a sentinel or a camera on a parking lot that is watching what's happening there. And it's not sending out anything interesting until your car is stolen. So the hippocampus is very sensitive to subtle changes that are important or could be important for the rest of the brain. And that seemed to be amplified by another mechanism, which is the sharp wave ripple. So now we're asking is that what is the content of this ripple? And then we find is that on trial 10, for example, this segment of the maze is replayed. On trial 25, this segment is replayed, and so on. And that's the explanation why the subtle differences that are read out by the sharp wave ripples in the waking state can do the selection. But then there should be a relationship between what the animal was doing during the trial and what it's doing now, and the ripples should be referring to the previous trial or the surrounding trial. So what I'm trying to convince you is that when you have a ripple, in this case in the blocks of trials, let's say in trial 10, then the probability that is replaying trial 10 is much higher than 25, 30 in this confusion matrix. Very distinctive. The confusion is very little. If the animal is running on trial 25, then our classifier said because of the Sharpe ripple is 25, the error is very little, that it could be reading out something. Now, it's not only reading distinct patterns, but the number of Sharpes that occur after each event is different. It depends on the animal's motivation, the number of the size of the reward, but in this case, everything was kept constant. So it's just the internal state of the animal that determines how many Sharpes I will emit after trial 5, trial 25, and so on. And you can see that this is an interesting distribution. In this trial, there was only one, and then this pattern on let's say trial 60 was replayed 10, 15 times. So the number of ripples that are occurring here are probably very important because we all know that episodic memories are funny because they are called one-shot learning. So we learn something once in an instant and we remember it forever. But it's cheating because those events could be replayed during the waking stage a couple of times. You are just not conscious of it. Now let's see what happens afterwards. So now we have this distribution. Of course, the exciting part of the experiments is when we put the animal back into its home cage. So we put the animal back into the home cage and we ask which of the trials will be more likely replayed during sleep ripples. And so in this case, this is an illustration so that I showed you previously that was trial 10. This was the awake ripple, and you look at the most probable replay during sleep, and you will say, oh, this was trial 10. And in order to quantify it, now I'm showing you the red one, which was exactly what I showed you before. This was the waking distribution of the Sharpes associated with the different trials, and subsequently, when the animal is sleeping in the home cage, the distribution is very similar. In fact, at the group level is super strikingly similar. No, just remember that in neuroscience, when you have a 0.07 correlation, then you open the bottle and you celebrate because it's so rare. And finding something like 0.6 or 0.8 is super rare. So to summarize what I had said so far, there are waking ripples that are markers, and there are sleep ripples that are consolidators. Now, I don't exactly know what the difference between the two, but a hypothesis could be something like this, and Maxim will correct me about this, that awake ripples are not embedded in the same neocortical states. There are no up and down states, there are no sleep spindles, and so on. So they may not be good for memory consolidation, but they may be good for tagging in the hippocampus and selecting a subgroup of neurons that will be in the hyperexcitable state for a while. And when sleep comes, then this event is replayed over and over again. In humans, young humans, sorry, in a person younger than 50 years of age, about 2,000 to 4,000 ripples occur every single night. So those are subconsciously organizing your brain very effectively, and I don't want to go further into how the categories are made and things like that, but it is a lot more elaborative process probably than what happens during theta when the animal is awake or when we are consciously awake. So to summarize the latter part, Sharpes are good. That's the only thing you have to remember. There are waking Sharpes that are doing the job for memory selection, and then the consolidation is done by Sharpe ripples during sleep. And so great assignment is done probably by many mechanisms in the brain, but I think my primary choice for episodic memory would be the hippocampus and hippocampal Sharpe ripples. Thank you.
you so much for that very insightful, intriguing talk. So I learned a lot, and
But
I'll try to remember it. I was especially intrigued by the effect of acetylcholine on the ripples. And also, then later in your talk, you talked about this period of about 10 seconds of some kind of oscillation on a 10-second period. And what intrigued me about that is if the acetylcholine receptors are metabotropic type, which type M1, 3, or 5,
M3, M1.
then they would be GQ coupled, G protein coupled receptors, and those create IP3, and IP3 calcium IP3 oscillations in cells, it has about a 10-second period. And so I wonder if there might be a connection between these different oscillation periods.
There must be. So both the 0.1, I call it 0.1 because of the bold written. There is another one that we discovered many years ago. It's 0.025. It's sometimes called ultra slow. I called it ultra slow, but later it's called infra slow and so on. The latter one is blood flow. The other one, it could be calcium. It could be a lot of things. And there is a lot of interesting debate has been going on for 3 decades, whether these are generated by the body or the brain. And the answer is both. You take a tissue culture, or you take a slice, and you get the 0.1-ish rhythm without subcortical neuromodulators. You can get also a isolated cortical slab, and you can get the 0.025. You go to the stomach has this rhythm, the heart rate has this stomach, the herring waves have been known for a long time, the superior cervical ganglion cells are controlling the precapillary arterioles. In other words, the autonomic system has a tremendous impact on the brain, which was maybe, I could say, undervalued for a long time. And now it's coming back because we realize that even the power of the alpha activity is affected very strongly, your decision-making process. And my students said, they are professors now at Cornell, they just had a paper last week in Science. They showed that the recent memories and the old memories are segregated as a function of phase of these ultra-slow oscillations. So it seems that they are beneficial,
well, you would think
and powerful. And every neuromodulator,
yeah,
they go.
And you would think that the purpose of the brain is to maybe to correlate the animal state with things that are happening in the environment, and the animal state includes every aspect of its bodily functions. And
I cannot agree more.
Without
Without the body, the brain is helpless.
Yeah.
Exactly.
Yeah, and it's important to, I did this thing over here in this place, and I got sick later, right? And maybe there's a connection between those. Yeah.
So one more word about acetylcholine or neuromodulators. So we showed Eric that there is a big discussion. What is a ripple? What is a fast gamma, and so on. It seems that the judge is acetylcholine. So when acetylcholine is high, there is gamma. In fact, there is a good correlation. When there is a ripple, the acetylcholine is low. So the biophysical mechanisms will tell you. Now, how do we do it in humans? I would say now it's pretty straightforward. You just look at the pupil diameter that goes hand in hand with everything else.
Beautiful. Thank you.
Talking about how can we remember as human beings, Terry sometimes says, bring to mind what you want to remember right before you go to sleep. But how can we apply some of these ideas to how humans learn and students are learning to kind of get things in memory better?
So, wonderful. If you look at Alzheimer's people, any neurological disease basically, or any psychiatric disease, especially at least in animal models, ripples are all pathological. They altered. Now, the problem, of course, is that's down deep in here. But the hope is that they are biased by the up and down states. So I can only cite a paper in connection with your question done by my ex-postdoc with Jan Born, is that they biased the up and down state with transcranial electrical stimulation in healthy German students. And they showed that as a result of entrainment of the down-up states, next morning they had a 10-15% gain in memory. I'm very hopeful because I have zero of those up and down states. And I don't have, well, I have a little bit, but stage 4 is missing after 60 years of age. And this is where the density of sharp wave ripples is higher. So maybe, indeed, with some external things we can increase. Of course, there is pharmacology and many other things.
Thanks.
Hi, great. I just want to ask a simple question. So slow waves during sleep, they propagate normally from most of the time from frontal cortex to more posterior. The up state is the one that propagates, and the down state occurs more or less synchronously across the whole cortex. Now, when you are looking on slow wave ripple coupling, by definition, in frontal cortex, you have to see your ripples more often during up state because it is longer. It starts there, propagates, and stays there, right? And in retrosplenial cortex, you are mostly in the down state. So I didn't see anything that you address that. You show some relation. Do you have any?
Yeah,
any
these are the other
comment on
figures.
that?
The other figures in the paper.
I didn't see, okay.
So what I'm telling you, you are absolutely right. You just pointed, you put your finger on the problem that happened over the past several years, as I mentioned, that you put an electrode here, said this is a cortical up and down state. And then you look at the hippocampus and you said, hippocampal ripples generate an up state. They do everything except they don't generate an up state. And it looks like that because the activity travels. If you put your electrode somewhere else, like the prefrontal cortex, then, or the Ampere and others, they always said, oh, it generates a down state. And that's why you have to record from all over the place, ideally together with the final input to the hippocampus, the entorhinal cortex, because the entorhinal cortex has a very beautiful down-up state transition with beautiful K complexes. Whatever down-up state travel makes it to the entorhinal cortex, that can bias the hippocampal ripples. The other way around is also true. The ventral hippocampal ripples are almost independent from the dorsal hippocampal ripples. And their anatomical projection is very different. Ideally, what you would like to have is, but Mark Schnitzer will sooner or later will do that, you look at the entire cortical mantle and the entire hippocampus, and then we can talk.
Yeah, great. Very technical question. How ripples are generated?
How?
How ripples are generated? Because cells do not fire at 200 hertz. Synaptic transmission is impossible at 200 hertz. I mean, all that. You can have one cell fire here, there, but...
So here you can do a nice modeling that we have done with Christoph Koch and said, what are the contribution of individual spikes? And very similar to your argument that the contribution of spikes nearby, enormous, but there are very few. You know, typically a pyramidal cell fires once, maybe a burst, and no more. But neurons that are surrounding about 150, 200 microns, they are numerous, and their contribution is tiny, but they add up in the extracellular space, and the ripples are nothing else, not nothing, but almost nothing else. The negative phase is superimposed spikes. They are mini population spikes. The positive dome could be a little bit of IPSP. At 200 hertz, 400 hertz, you know, those fast ripples, I don't see any physiology for that, except gap junctions.
Thank you.
Хорошо.
A criticism, perhaps ineloquent, is that a lot of the work that is done in this field is correlational. Essentially, you know, that how do we know that these oscillations themselves are selecting for assemblies rather than just being a byproduct of some underlying process that is selecting for these assemblies? You know, you mentioned the acetylcholine work perturbing ripple oscillations in mice, and I'm just wondering in general if you could comment on work that can be done to demonstrate sort of a more causal relationship between these ripple oscillations and the selection of relevant cell assemblies.
So that has been a little bit done prior to this work. People have done, they killed ripples like Laurent Frank and others during waking. We did the same kind of thing. And indeed, there is no selection, there is no consolidation because nothing was selected. So that part is done. What more you can do is, reflecting to your more fundamental question, I devoted a book to that, but the short answer to that is every known oscillation in the brain is inhibition-based. So this is a mechanism to segment messages into short and longer ones, which is the fundamental requirement for any communication system. There's no way I could give in this talk in one long word. You have to parcel them into shorter and longer messages. And this is what probably the most important contribution of the different types of oscillations. There are not only there are many, they form a hierarchical system through a mechanism called amplitude phase coupling. So if you are looking for a neural syntax, that is what determines the length of messages, your best bet is brain oscillations. If you know a substitute, let me know. There are substitutes if you have an external synchronizer. For example, in a bat, there is no theta, but they have wing laps, and they synchronize the hippocampal activity. In primates, there is no real convincing theta. I try to believe it because I'm a big fan of theta, but I don't see evidence. But we see saccadic eye movement triggered activity. And saccades happen to be when you focus on something, as Pascal Fries, the intersaccade intervals are log-normally distributed. But when you focus on something, you see that it's about 4 hertz. So it's an evoked series of activity, but it has the same function, which is timing. It gives you the beginning and the end of the message. If you don't have that luxury, don't have the external timer, the brain makes it up. That's my long answer to your question.
Thank you.
Mm-hmm.
Hi, thanks for the talk. Super cool stuff. You mentioned the role of ripples for tagging for later in sleep. Could you comment a little bit about what is known and the interpretation of what awake replay and also theta sequences could be doing, except for anything that could be just tagging for later, like influences in the decision making?
So another student of mine, Michael Zugaro, who is in the College of France, addressed this question and said, this is the link between waking and waking ripples, waking theta and waking ripples, and said if there is no sequence during theta, because you got rid of it, there will be no ripple content, or it will be gibberish. So indeed, the priming can occur during the waking state also. Usually it's a very short segment, and it is giving you a 30 centimeters travel distance. So every single theta cycle, the past is there, you move forward, and then you move forward, and so on. During ripples, it's a much longer and more fragmented. So what it does is a different type of combination of information rather than a sequential activity. So there are beautiful human studies. You can criticize whether those are real ripple-related from Tim Barron's laboratory at UCL in human MEG studies, and they say, what is being replayed is not the physical trajectory of the animal, including the human, but what is prioritized by the brain consciously or subconsciously. And what they did, they trained particular rules. The rules told you what is the value of certain things, and the things that have a higher utility will be replayed more frequently.
Okay, thank you.